Hello, today I'm reading another paper. This one is called Fast is Better Than Free, Revisiting Adversarial Training. It's from Carnegie Mellon University and Bosch Center for Artificial Intelligence in Pittsburgh. Abstract. Adversarial training, a method for learning robust deep networks, is typically assumed to be more expensive than traditional training due to the necessity of structuring adversarial examples with a first-order method like projected gradient descent, PGD. In this paper, we make the surprising discovery that it is possible to train empirically robust models using much weaker and much cheaper adversary, an approach that was previously believed to be ineffective, rendering the method no more costly than standard training in practice. Specifically, we showed that the adversarial training with fast gradient method, FGSM, when combined with random initialization, is effective as PGD-based training but has significantly lower cost. Furthermore, we show that FGSM adversarial training can be further accelerated by using standard techniques for efficient training of deep neural networks, allowing us to learn a robust cipher-10 classifier with 45% robust accuracy to PGD attacks with epsilon equals to 8 divided by 255 in 6 minutes, and a robust ImageNet classifier with 43% robust accuracy epsilon equals to 2 divided by 255 in 12 hours. In comparison, past work based on the free adversarial training, which took 10 to 50 hours to reach the same respective thresholds. Finally, we identify a failure mode referred to as catastrophic overfitting, which may have caused previous attempts to use FGSM adversarial training to fail. All code for reproducing the experiments in this paper, as well as trained model weights, are at GitHub fast_adversarial. Introduction. Although deep network architectures continue to be successful in a wide range of applications, the problem of learning robust deep networks remains an active area of research. In particular, safety and security focused applications are concerned about robustness to adversarial examples. Data points have been adversarially perturbed to fool a model. The goal here is to learn a model which is not only accurate on the data, but also accurate on adversarially perturbed versions of the data. To this end, a number of defenses have been proposed to mitigate the problem and improve robustness of neural network, with some of the most reliable being certified defenses and adversarial training. However, both of these approaches come at non-trivial additional computational costs, often increasing training time by order of magnitude over standard training. This has slowed progress in researching robustness in deep networks due to computational difficulty in scaling to much larger networks and inability to train models when experimenting with new ideas. In response to this difficulty, there has been a recent surge in work that tries to reduce complexity of generating an adversarial example, which forms the bulk of the additional computation in adversarial training, Zhang 2019. While these work present reasonable improvements to the runtime of adversarial training, they are still significantly lower than standard training, which has been greatly accelerated due to the competitions for optimizing both the speed and cost of the training, Coleman 2017. In this work, we argue that adversarial training, in fact, is not as hard as has been suggested by this past line of work. In particular, we revisit one of the first proposed methods for adversarial training using the fast gradient sign methods to add adversarial examples to the training process, Goodfellow 2014. Although this approach has been long dismissed as ineffective, we showed that by simply introducing random initialization points, FGSM-based training is as effective as projected gradient descent-based training, while being an order of magnitude more efficient. Moreover, FGSM adversarial training and to the lesser extent other adversarial training methods can be drastically accelerated using standard techniques for efficient training of deep networks, including cyclic learning rates, mixed precision training, and other similar techniques. The method has been extremely few has extremely few free parameters to tune, and can be easily adapted to training procedures. We further identify a failure mode that we can call catastrophic overfitting, which may have caused previous attempts at FGSM adversarial training to fail against PGD-based attacks. The end result is that with these approaches, we are able to train empirically robust classifiers far faster than in previous work. Specifically, we train an L-infinite robust sci-fi 10 model to 45% accuracy at epsilon equals 8 divided by 255, the same level attained in previous work, in 6 minutes. Previous papers reported times of 80 hours for PGD-based training and 10 hours for more recent free adversarial training methods, 2019. Similarly, we train an L-infinity robust ImageNet classifier to 43% top 1 accuracy at 2 divided by 255 epsilon. Again, matching previous results in 12 hours of training compared to 50 in the best reported previous work that we are aware of, 2019. Both of these times roughly match the comparable time for quickly training a standard non-robust model to reasonable accuracy. We extensively evaluate these results against strong PGD-based attacks and show that they obtain same empirical performance as the slower PGD-based trainings. Thus, we argue that despite the conventional wisdom, adversarially robust training is not actually more challenging than the standard training of deep neural networks and can be accomplished with the notoriously weak FGSM attack. Related work. After the discovery of adversarial exemplar by Zgd et al. 2013, Goodfellow et al. 2014, proposed fast gradient sign method to generate adversarial examples with a single gradient step. This method was used to perturb the inputs to the model before performing backpropagation as an early form of adversarial training. This attack was enhanced by adding randomization step, which was referred to as R plus FGSM 2017. Later, the basic iterative method improved upon the FGSM by training multiple smaller FGSM steps, ultimately rendering both FGSM-based adversarial trainings ineffective, 2016. This iterative adversarial attack was further strengthened by adding multiple random restarts and was also incorporated into adversarial training procedure. These improvements form a basis of what is widely understood today as adversarial training against projected gradient descent adversary, as the resulting method is recognized as an effective approach for learning robust networks, 2017. Since then, PGD attack and its corresponding adversarial training defenses have been augmented with various techniques such as optimization tricks like momentum to improve the adversary, 2018, combination with other heuristic defenses like matrix estimation, 2019, or logit pairing, 2018, and generalization to multiple types of adversarial attacks, 2019. In addition to adversarial training, number of other defenses against the adversarial training has also been proposed. Adversarial defenses span wide range of methods such as preprocessing techniques, 2017, detection algorithms, 2017, verification and provable defenses, 2017 and 2018, and various theoretically motivated heuristics, 2018. While certified defenses have been scaled to reasonably sized networks, 2018-2019. The guarantees don't match the empirical robustness obtained through adversarial training. With the proposal of new defense mechanisms of great concern in the community is to use the strong attacks for evaluating robustness. Weak attacks can give misleading sense of security, and the history of adversarial example is related with adversarial defenses. which were ultimately defeated by the strong attacks. This highlights the difficulty of evaluating adversarial robustness, as pointed out by other work which began to defeat the proposed defenses en masse. Since then, several best practices have been proposed to mitigate this problem. Despite the eventual defeat of other adversarial defenses, adversarial training with PGD adversary remains robust to this day. However, running a strong PGD adversary within an inner loop of training is expensive, and some earlier work in this topic found that taking larger but fewer steps did not always significantly change the resulting robustness of the network. To combat the increased computation overhead of the PGD defense, some recent work has looked at the regressing of the k-step PGD adversary to a variation of single-step FGSM predecessor called free adversarial training. Which can be computed with little overhead over the standard training by using a single backwards path simultaneously to update both model weights and also the input perturbation. Finally, when performing the multi-step PGD adversary, it is possible to cut out the redundant calculations during backpropagation when computing the adversarial examples as additional speedup. Although improvements are certainly faster in the standard adversarial training procedures, they are not faster than traditional training methods and can still take few hours to days to compute. On the other hand, top performing training methods from Dawn bench competition are able to train Cypher10 and ImageNet architectures to standard benchmark metrics in mere minutes and hours respectively, using only a modest amount of computational resources. Although some of the techniques can be quite problem-specific for achieving bleeding-edge performance, more general techniques such as acyclic learning rates and half-precision computations have been quite successful in the top-ranking submissions and can also be useful for adversarial training. Adversarial training overview. I will now a little bit speed up. I will not read every piece of text, but I will go a little bit faster. Adversarial training is a method for learning networks which are robust to adversarial attacks. Given a network f theta parameterized by theta, dataset xi, yi, and a loss function L, and a threat model delta, the learning problem is typically cast as the following robust optimization problem: minimum over theta, sum over I, maximum delta in small delta in big delta. Loss function is as a function of f theta as a function of xy plus delta, comma y I, end of the bracket, end of the loss function. A typical choice for a threat model is to take delta equals to as a set of infinite norm of small delta is less than epsilon for some epsilon bigger than 0. This is the L infinite threat model used by Madre et al. 2017 and is the setting we study in this paper. The procedure for adversarial training is to use some adversarial attacks to approximate the inner maximization over the delta, followed by some variation of the gradient descent on the model parameters theta. For example, one of the earliest versions of the adversarial training used the fast gradient sign method to approximate the inner maximization. This could be seen as a relatively inaccurate approximation of the inner maximization L infinite perturbations, as the following closed form Goodfellow 2014. Delta star equals epsilon times sine gradient over x of a loss function, which is a function of f, which is a function of x, and of the function f, comma y, and of the loss function gradient and the sign. Better approximation of the inner maximization is to able to multiple small FGSM steps of the size alpha instead. When the iterate leaves the thread model, it is projected back to the set delta for L infinite perturbations. This is equivalent to clipping delta to the interval minus epsilon to epsilon. Since this is the only local approximation of non-convex function, multiple random restarts within the thread model delta typically improve the approximation of the inner maximization even further. A combination of all of these techniques is known as PGD adversary. Okay. Okay, I'm gonna skip these algorithms. Actually, let me try to describe them. Algorithm 1, PGD adversarial training for t epochs given some radius epsilon, adversarial step size alpha, and n. PGD steps in a dataset of size m for a network f theta. For t from 1 to big T, do for I equals in 1 to big M, do perform gradient adversarial attack delta equals 0 or randomly initialized. For j from 1 to n, do delta equals delta plus alpha times sine of gradient over delta of loss function of the function network xi plus delta comma y. Delta equals maximum of minimum delta and epsilon comma minus epsilon. And for over j, theta equals theta minus gradient over theta, loss function, network function xi plus delta, comma y, update model weights for some optimizer SGD. I will just quickly read the free adversarial training for the epochs, and so on and so on. Iterate over 10 divided by n times to account for minibatch replays and run for t total epochs. Perform simultaneous FGSM adversarial attack and model the weight updates t times. Compute gradients for perturbations and model weights simultaneously. Update the model weights with some optimizer SGD. Okay, fast adversarial training. To speed up the adversarial training and move towards the state of the art in fast standard training methods, we first highlight the main empirical approach contribution of this paper. FGSM adversarial training combined with random initialization is just as effective as defense as PGD-based training. Following this, we discuss several techniques from Dawn Bench Competition 2017 that are applicable to all adversarial training methods, which reduce the total number of epochs needed for convergence with cyclic learning rates and further speed up computation with mixed precision arithmetic. So algorithm 3, FGSM adversarial training for t epochs given some radius epsilon and PGD steps, step size alpha and dataset size m for network f theta. For t between 1 and t, do. For I between 1 to m, do. Perform FGSM adversarial attack. That is, delta equals uniform minus epsilon to epsilon. Delta equals delta plus alpha times sine gradient over delta, loss function f theta, xi plus delta, and y. Delta equals maximum, minimum, delta, epsilon, and minus epsilon. Theta equals theta minus gradient over theta, loss function, etc. That is, update model weights with some optimizer, for example, SGD. Okay, so what they do here, let me have a look. So they uniformly initialize delta between minus epsilon to epsilon. then I guess this second delta is actually in vector, which you cannot actually see, so that, I don't know. No, probably not. Okay, so delta then equals delta plus alpha times signature of gradient over the change of x of delta. So they make a change in the input of size, of this delta vector. They make a gradient of that loss function with delta, and then they apply a sine function and over that. Okay, so they basically just get some sort of directions from that. Each, I guess the sign, they mean that they take the vector, the gradient produces the vector, and they only truncate that to the sign of each of the values of the vector, and then they make a very small step with this alpha. That's the step size, and they add it to the delta. Then they do maximum minimax over delta and epsilon and minus epsilon. So basically they make sure that the delta is not going outside of the epsilon size, some sort of epsilon ball, right? And I guess epsilon ball in Manhattan, or max distance, I guess this infinite distance, right? And then theta, then they update theta. Yeah, and then they update theta with stochastic gradient descent. Effectively, they update the model weights with some optimizer based on that. All right. Okay. Revisiting FGSM adversarial training. Despite being quite similar to FGSM adversarial training, free adversarial training is empirically robust against PGD attacks, whereas FGSM adversarial training is not believed to be robust. To analyze why, we identify key difference between the methods. A property of free adversarial training is that the perturbation from the previous iteration is used as the initial starting point for the next iteration. However, there is little reason to believe that the adversarial perturbation for a previous mini-batch is a reasonable starting point for the next mini-batch. As a result, we hypothesize that the main benefit comes from simply starting from non-zero initial perturbation. In light of this difference, our approach is to use FGSM adversarial training with random initialization for the perturbation, as shown in the algorithm 3. Okay, so this is the algorithm that we saw, and the random initialization step is this uniform delta I was mentioning. And yeah, the reason is that they don't wanna, they think that using the previous perturbation, which we already adapted the model for, it makes no sense, and they always do some random initialization for each batch, I guess. Okay, let's go here. Crucially, we find that starting from non-zero initial perturbation is primary driver for success, regardless of the actual initialization. In fact, both starting with the previous mini-batch perturbations or initializing from uniformly random perturbations allow FGSM adversarial training to succeed at a robust full strength PGD adversary attacks. Randomization is not a new idea. It was previously studied 2017. They used different restricted random initialization data, which does not result in models with full strength of PGD adversaries. Okay, and they give a more detailed comparison in appendix. Okay, then here FGSM step size, computational complexity. A second key difference between FGSM and free adversarial training is that the latter uses single backward pass to compute gradients for both the perturbations and the model weights while repeating the same mini-batch m times in a row, called mini-batch replay. In comparison, FGSM adversarial training does not need to repeat the mini-batches, but needs two backward passes to compute gradients separately for the perturbation and the model weights. As a result, the computational complexity for epoch of FGSM adversarial training is not truly free and is equivalent to 2 epochs of standard training. So downbench improvements. Cyclic learning rate, mixed precision arithmetic. Figure 1. Cyclic learning rates used for FGSM adversarial training on Cipher 10 and ImageNet over the epochs. ImageNet cyclic schedule is decayed further by a factor of 10 in the second and third phases. Okay, Cipher 10, they go from 0 to some value and then they descend. ImageNet, so. Okay. So these are learning rates. So they start with a very small learning rate, then go to some big value, and they generally descend. Experiments, verified performance on MNIST. Since FGSM attack is known to be significantly weaker than PGD attack, this is understandable if a reader is still skeptical of the true robustness of the method trained using this method. To demonstrate FGSM adversarial training confers real robustness to the model. In addition, developing against PGM adversary, we leverage mixed integer linear programming methods from formal verification to calculate an exact robustness of a small but verifiable models. Okay, so FGSM, PGD and free, so we have free graphs, all have very, very similar data points, except in the free, for the free model, there's significantly more steps, I guess. Performance of the model trained on Cipher 10 at epsilon 8 divided by 255 with cyclic learning rates and half precision, given varying number of epochs across the different adversarial training models. Each point denotes the average model performance over 3 independent runs, where x-axis denotes the number of epochs n to the model it was trained for, and y-axis denotes the resulting accuracy. The orange dot measures the accuracy on natural images, and the blue dots plot the empirically robust accuracy on adversarial examples. The vertical dotted line indicates that the minimum number of epochs needed to train the model to 45% accuracy. Okay. Fast Cipher 10. So then we have more results. Catastrophic and overfitting. While FGSM adversarial training in the context of this paper, many other researchers have tried and failed FGSM adversarial training to work. In addition to using a zero initialization or too large a step size as seen in table 1, other decisions like specific learning rate schedules on the number of epochs for the training procedures can also make it likely for FGSM adversarial training to fail. However, all of these failure modes result in what we call catastrophic overfitting, where the robust accuracy with respect to PGD adversary suddenly drops to 0% on the training data. Due to the rapid deterioration of the robust performance, these alternative versions of FGSM adversarial training can be salvaged to some degree with simple early stopping scheme by measuring PGD accuracy on small mini batch of training data. And the recovered results for some of the failure modes are shown in table 1. Catastrophic overfitting and the early stopping scheme are discussed in more detail in Appendix D. Alright, so yeah, they admit catastrophic overfitting is possible, and they just solve it by early stopping. Takeaways from FGSM adversarial training. While it may be surprising that FGSM adversarial training can result in a robustness to full PGD adversarial attacks, this work highlights some of the empirical hypotheses and takeaways we described below. Adversarial examples need to span entire threat model. One of the reasons why FGSM and FGSM, as done by 2017 Tramer, have failed due to the restricted nature of the generated examples. The restricted, or the lack of initializations in perturbations which perturb each dimension by either 0 or plus or minus epsilon, and so adversarial examples with feature perturbations in between them are never seen. Okay. Let's see. Defenders don't need strong adversaries during training. This work suggests that the rough approximations for the inner optimization problem are sufficient for training. This in contrast to the usage of strong adversaries at evaluation time, where it is standard practice to use multiple restarts and a large number of PGD steps. Conclusion. Our findings show that FGSM adversarial training, when used in a random initialization, can be just as effective as the more costly PGD adversarial training. While a little iteration of FGSM adversarial training is double the cost of free adversarial training, it converges significantly faster, especially with the cyclic learning rate schedule. As a result, we are able to learn adversarially robust classifiers on Cypher-10 in minutes and for ImageNet in hours, even faster than free adversarial training, but with comparable levels of robustness. We believe that leveraging these significant reductions in time to train robust models will allow future work to iterate even faster and accelerate research into learning models which are resistant to adversarial attacks. By demonstrating that extremely weak adversarial training is capable of learning robust models, this work also exposes the new potential direction in more rigorously explaining when approximate solutions to the inner optimization problems are sufficient for robust optimization and when they fail. So this is the end of the video. Thank you for listening and hopefully see you next time.